This is the concept of independence. Two events are independent. So I guess I should call these two events A and B. So two events A and B are independent if the outcome of one event has no effect on the outcome of the second event. So whatever happens in event A has no effect on B. So I'll give you some examples. Suppose event A was throwing a coin and you're getting ahead. So that's what event A was. And suppose B was you roll a dice and you get a 3. Would you agree that those two events have no interconnection? They do not affect each other in any meaningful way. Those two events are considered to be independent events. Let's do another one. Suppose we had 5 people. And the teacher written said, event A and event B. Here's my two events. So make this, it's a little bit complicated, but here goes. I am going to randomly pick one person in the class and give them $10. So event A is the first person picked. Was, let's say, D, right? So the first person I picked was Donald, right? That's event A. I picked Donald. I give him $10. And then I randomly pick a person from the class. And I'm allowed to pick anybody because I'm just going to shut my eyes and say, you. And the first person that I picked was Donald again. Those two events are independent. The fact that you picked me the first time had no effect on my chances of being picked the second time, because wasn't it just shut your eyes and pick somebody? And couldn't I have picked D just as easily as anybody else? Would you agree in that situation then, since this event, what happens in A did not affect the chances of B happening? That's what we call independent. So it's a little bit less obvious, but it's still considered independent. Now here's a third story. A, B, C, D, and E. And A is going to be the first person picked. Was me. Yes, I shouldn't have called that first, shouldn't I have called that second? That's better. And this time, the second person picked was D. But I'm changing the rules in this second story. In the second story, I randomly pick somebody, and it's going to be Donald, and I give him his $10. I say, okay, Donald, you sit at the back of the class. You only pick from what's left the second time. Would you agree that the chances now are definitely related? In fact, isn't that impossible if that happened? So this is what we call dependent, although I think the book calls it not independent. That's fine. And this is independent, and this is independent. Okay. So that is the concept of independence. If two events A and B, the effect of one has no effect on the outcome of the second event, then they're considered to be independent events. When things are independent, then the following is true. The probability that you have A and B happening is simply just the probability of A times probability of B. So for instance, see if A was getting ahead when you throw a coin and B was rolling the number 3 on the dice. Since these are independent, the probability you get ahead and you rolled a 3 is the probability of you got ahead times the probability that you get a 3. Chance that you get ahead is 1/82. When you roll a dice, the chance that you get a 3 is 1/86. The combined probability then is 1/12. So if two events are independent of each other, then you can find the probability of both of them happening, right? A and then B happening by simply just multiplying them together. And it's called in the textbook, I think it's called the multiplicative rule or the multiplication rule. I believe I did a list of all the cards. Is that correct? Clubs, diamonds, good. Because I want to do a card question and show you a little bit. Although I get a feeling I may have done this one. What's the probability that you get a heart and a king? Now, those two events are not independent. Aren't some hearts kings? So if I got a king, it would definitely be a thing. So we know there are 52 cards. And I've just used the word and, I apologize. Or heart or a king, right? There are 13 hearts and there are 4 kings. You remember doing this kind of question? But that's not the correct probability. Isn't there double dipping going on? How many cards are, in this case, kings and hearts at the same time? Just one. And so you would get, in this case, 60, 90, 52, which if you take a 4 into it, you get 4 13s. Okay. I think I've caught up. We did compliments, I'm sure of that. I remember talking about those. Right. Did we do question 9? Because that's where I want to start if we haven't. That's the one to do with 6 prizes in cereal boxes. Have we done that question? Right, that's perfect. I now know, I believe we'll be finished off. So let's look at some homework questions and how we deal with them. A brand of cereal contains a prize in every box, and there are 6 possible prizes, right? You get a whistle, you get, whatever it is, right? Things like that. Each of the prizes is equally likely to be in any of the boxes. If you purchase 2 boxes, what's the probability that you receive the same prize in both boxes? So I'm going to go for independence here. Would you agree that if whatever you get in one box, isn't it going to have no effect on what is in the second box? Couldn't they just be the same or different and there's no connection, right? It's not like the first box whispers to the second box, hey, you better get out of here, I'm already a whistle, there shouldn't be 2 whistles, right? There's no connection. And because of that then, can't we calculate the probability that 2 boxes will have the same prize in each, right? And let me, no, I'm not there. Go away. I've lost you. Damn it, the windows in this thing. Right. So here we go. First thing I'm going to do is realize what's the probability that I get. I'm just going to call the prizes A, B, C, D, E, and F, right? 6 prizes. A is a whistle, right? So this would mean getting a whistle in both, right? Both boxes had whistles. Now, since they're independent, can't you go the probability of A times the probability of A? And what does that get me? Well, that gets me 1/6, because that's the chances of that, times 1/6, and that gets me 1/36. So the chances that both of them are A is 1/36. But couldn't they both be a B, both be a C, both be a D, both be an E, and finally both being an F? So the probability that both are the same is both of them being A's or B's, or all the way to both being F's. What do you think the probability of getting both of them B's would be? I don't actually need to calculate it. What would that answer be?
1/36.
That'd be the same.
Yeah, and would you agree it would be the same for the C, the D, the E, and the F?
Absolutely.
Now, I'm writing this out the long way. Can you see that there'd be a much quicker way to write in this calculation? Can I just say it was 6 lots of 136? 6 separate events all being added that just happen to have the same probability. And after all that hard work, the chances that you get the same prize in each box, right, is going to happen 186 times. And that's the answer to question A. And then question B says, what's the probability that you get different?
Wait a minute, Professor, you just lost me. Did you say the probability that you're gonna get the same in both is 1 out of 6?
Yeah. Because you could get both of them being A, or both of them being B, or both of them being C, all the way to both of them being F. And when you combine all of those together, the chances that both of them are the same is quite high. It's 186. Interesting. Surprising, maybe, but that's what it is.
Yeah. I thought you had multiplying.
I did. 6 times 1/6 is the same as adding up the same thing 6 times. I'm just trying to make my calculation easier.
Okay.
And you could miss that line out and it would jump right to here. Right, what's the probability that they're different then? And don't try and count out all the different ways that you could get difference, because that would give you a sore head. There's a much quicker way of doing it. Both the same. I guess I should put the word in here. Both different. Do you recognize that these are complements of each other?
1 out of 3.
Not 1 out of 3, no. This and this are complements of each other. Remember complements, opposites? What do opposite probabilities always add up to? So if this is 1, won't that guy be the other 5, 6?
Yeah.
Right. So if something happens and it's got a probability of 1/3, its opposite, its complement, would be the other 2/3. If something is a 1/10, the other part would be 9/10. So we're using the fact that we had to calculate this the hard way, but the opposite event, both being different, is opposite of both being the same, right? Is just what's left from 1, because these are the complements. If I call this A, then I would call this A complement. And I'm using the probability of A plus the probability of its complement always equals 1. I'm using that property to figure out if this is a 5th, then that had to be the rest. That makes sense now? Okay. Now, next question, which you can't see, but I'll read it out to you because it'll save all this jumping back and forward, is a fair coin. Right, that means nothing weird about it, just a normal coin. And here are some events. We have A, you get a head on the first throw. And you're going to take this coin and you're going to throw it 2 times. And B is the event that you get ahead on the second throw. Okay. Let's find some probabilities. What is the probability that you get ahead on the first throw? So you just throw one coin in the air, right? What's the
50%.
probability that you get ahead?
50%.
Okay,
One
I'll
half.
call that a half, but you're right. What's the probability that the second throw you also get ahead? Would you agree that's a half? Now, what's the probability of A happening and B?
1/4.
And can't we, you're right, can't we do the multiplication rule? Would you agree that what happens on the first coin has no effect on the probability of the second coin being ahead? And because they're independent, you can multiply them together. And I hope that's what you're thinking when you said a quarter. Did that kind of the way it works? Do you see that this multiplication rule is quite helpful for probabilities that get quite complicated? You know, suppose I said, oh, I'm going to throw a coin 4 times. What's the chances that I get head, 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 and head, right? Well, isn't it much easier just to say, well, they're independent, a half times a half times a half times a half, right? Dead easy. If you didn't use that property, wouldn't you have to figure out all the different ways that 4 coins could happen and then just count, you know, the one that worked against all the others that didn't? Now, be a little bit careful about this one. What do you think the answer to that last one is? This is question D.
Probability is 1 because it's going to be adding them together. Anything could happen. Either one's fine.
Okay. So I'm hearing the answer that it will be 1. Any other suggestions for what it might be?
Would it possibly be 1/2 because it's a 50% chance either one could happen?
It could be. Is there any other possibilities? Obviously, I wouldn't be doing this if the right answer had already been said. Okay, here goes. Now, let me try and prove it to you. The probability of A or B is the probability of A added to the probability of B, which is what Robert was saying. Take away the probability of A and B. So if you have 2 events and they are independent of each other, this is the formula that you would use to calculate the OR. Now we know that that guy's a half, we know that guy's a half, and we know this guy is a quarter. Can you see where the 3/4 came from? So you might be thinking, well, why isn't it just, you know, why isn't it just 1? Well, isn't there a possibility that both of them were tails? If you write this down in English, wouldn't that be, what's the probability that the first one was ahead, or the second one was ahead, or both of them were heads? Well, isn't that only 3 out of 4? Isn't there still a tail and a tail missing? The 4th one near the pit. So that's formula catches those. So if 2 events are independent, here is how you can calculate the A or B version? Okay, that was a good question. Sneaky, but good. So question 11 is going to be a story about you have two friends. So A is going to be your first friend, born on a Friday. And B is going to be that your second friend was born on a Friday. Okay. So let's see what happens. What is the probability of A? It's going to be our first question. What is the probability of B, which is going to be your second? And your third one is going to be that one. Now, they don't have a D, but I'm going to put one in. Let's make an assumption. Are these two events probably going to be independent? Right? If your first friend is born on a Friday, does that have any effect that your second friend might be born on a Friday as well? There shouldn't be a connection. So independence is important here. Now, what's the chance that you pick someone and your friend was born on a Friday? Would you agree that's probably a 1 in 7? Wouldn't it be the same for your second friend? Now, if you want to do an and, because they are independent, can't you just use the multiplicative rule? So far, so good. A and B, 1/7. A times probability of the old. Now, A or B is probability of A, probability of B, take away A and B. 1/7 plus 1/7, take away 1/49. And that one I'm not even going to try and do. I'm just going to go 1/7 add 1/7, take away 1/49, and let the calculator tell me that it's 13/49. So if you have to do with two independent events and just multiply them together. If you want to do an or with two independent events, then you need to use this formula, which is the first guy plus the second guy, take away the and, the both. You feel a little bit more comfortable about that? Right. So probability isn't always as intuitive as you in some cases at least. Okay, this is question 12. A popular lottery game is one with 3 digits. Ooh, 3 digits. A is going to be that the first digit is odd. Okay, that's that event. B is going to be that the first digit is even. And C is that the second digit is back to being odd. Okay. So you imagine you've got 3 digits, right? 1, 2, 3. That's the first digit, right? The second digit, the third digit. So, you know, people might say, I like 1, 2, 5. That's my lucky number. And if it comes up, you win some money. Not big bucks, but you win some money. Okay, so what is the probability that the first digit is odd? How many digits are there? We're talking about just a single digit. How many digits are there? Because that's the bottom. And how many of those are odd? That's the top.
Would it be 4 out of 9.
Count 0 as even. What does that change your answer to?
5 out of
Five.
9.
5 out of 10.
Yes.
1, 2, 3, 4, 5. I've run short room. 6, 7, 8, 9. There are 10 digits, 0 counts, and 5 of them are odd out of 10. So that becomes a half. What's the probability of B then?
It'd be 1/2 again.
Would be 1/2 again. Before I talk about C, are A and B independent events? If the first digit is odd, does it have any effect on the first digit being even?
No.
Well, if the first digit is odd, can the second digit even be even? Sorry, I'll rephrase that. First digit is odd. Can the first digit also be even at the same time?
No,
No, and they're worse than being independent, aren't they? One stops the other one from happening. Right, so those are not independent events. Now, how about the first digit being odd and the second digit being odd? Are they independent events? Yeah, first digit could be
No,
3, right?
oh.
And the second one could be 7, right? Or 9 or whatever it wants to be.
okay.
Right. So independent, one has no effect on the other. Dependent, they interfere in some way. So we are going to be doing an A and a C. Oh, actually, this is question D. Probability of A and a C. Now, we've already decided that these are independent, so can't they just be 1/2 times 1/2 and you get a quarter? You happy about multiplying them to get the and? In question, I know I'm jumping around a little bit. In question F, they want us to find an A or a C. Now, when you see an or and it's independent, can't we use the P of A plus the, P of B, take away the and? And what do we get? Well, the probability that it's A is 1/2, and that's a C, is 1/2. Take away a quarter. Oh, it's that 3/4 that we had. Now, this one's a sneaky one. A and B are dependent. What's the probability that you get the first one's an odd and at the same time, the first one is even? It's a trick question. Yeah, it's 0. Now, what other ones have I missed? E. What is, I've done A and C. Oh, so that was E. No, I'm getting my letters on. Okay, this is question E. What's the probability of A and? No, I've done that. What in the heck have I missed then? Oh, I haven't done A or B. Well, A or B. Again, this one, they are dependent. So when they are dependent, you can't use this formula and you can't multiply them together, right? It's only when they're independent events that you can use the multiplication rule to get the and this rather ugly formula to get the ors. When they are dependent, you have to take it on its values. And I think, Robert, you gave the answer to a question like this earlier on. What's the probability that the first one is an odd or the first one is even? And it's a trick question.
Wouldn't it be 1/2?
No. First one is odd or the first one is even. It's not going to be a half.
Just one, because it can
Just
be
one.
either or.
Right. So do you see, that's where the either or happens. It happens when the two things are dependent on each other. But you see how the or works when they are independent events. You have to take away this little guy. It's kind of like taking away, it's not really the same, but analogous to taking away the double dip, right? You're taking away a bit where both can happen at the same time. So are we getting a little bit more comfortable about the A or B kind of story when they're independent? And as long as you make that decision, then your life is going to be a lot easier, I believe. We're now going to enter a new topic. Conditional probabilities. These ones you have to be really careful about because they change the rules a lot. This is the general way in which a conditional probability is written. You read it out loud as the probability that A happens given that B already has happened. So you read this out as probability of A given B. That's how you would say it out loud. You'd say probability of A given B. And a little bit more expanded version, the probability that A happens given that B has already happened. So imagine that we do a card story. And I say to you, what's the probability that you get a heart? And we'll call that guy A. Well, there are 52 cards in a deck, 13 of which are hearts. Nothing too surprising. Probability is a quarter. Now, let's suppose that this was some kind of gambling game and the guy that was about to give the card was about to flip it over, but you caught a quick look at it and you found out it was red. Couldn't get any more than that, but you knew it was red. You would write the probability of A given B, and it would be written something like this. What is the probability that it's a heart, given that you know it's a red card? That affects the probability a lot. The minute you give someone some extra information, that's what conditional probability is designed to cope with. The minute you give them some extra information, you can alter the probability of something happening. Would you agree that the chances of getting a heart are now better now that you know that it's red? So let's see how that affects the probability. The guy on the bottom is red. So doesn't that mean that there's now only 26 possibilities? The 13 diamonds and the 13 hearts. Now, out of those 26, aren't 13 of them hearts? Can you see in this case, the probability has gone up to a 50-50 chance? What about this one? The probability that you get a heart given that it was a black card. Well, since you know it's a black card, there's 26 of those. How many of those 26 black cards, that's clubs and spades, how many of those are hearts?
0.
Can you see that conditional probabilities can make things really altered a lot, right? That's what it would be if you knew nothing. If you know it's a red card that's happening, it's a half. If you know it's a black card, you know it's 0. What about this one? What's the probability it's a heart, given that it was a king? Let's suppose you noticed it had a face, but you couldn't see anymore. What is the bottom, the denominator, going to be, given that it's a king? So you know it's a king. So how many kings are there? 4. Of those 4 kings, How many are hearts? Just one. Wait a minute. Isn't that just the same answer as that one? If you're told that it's a king, doesn't have no effect on the chances of it being a heart. It doesn't help it. It doesn't hinder it. It basically doesn't help you at all. Couldn't you just say, what's the probability that you get a heart given that it's a Tuesday? Right, I'm telling you a piece of information, but aren't I telling you a piece of information that doesn't change the probability of getting a heart? So conditional probabilities are important. Let's try another one. I like cards because I get more opportunity. What's the probability that you get a face card? Right, there are 52 cards and there's 3, 6, 9, 12. There's 12 out of that. So if I divide top and bottom by 4, right, I get 3/13. Are we good? Right. Now, let's play about with some of these conditional probabilities. What's the probability that you get a face card given that it was a king? Well, since you know it's a king, have you noticed that the piece of information tells you the bottom number? How many of those 4 kings are face cards? All of them. So isn't that probability 1? Let's switch places. What's the probability that you've got a king given that it's a face card? Well, if I tell you it's a face card, there are 12 of those. How many of those 12 face cards are a king? Do you see that those two probabilities are not even vaguely similar? They're quite different from each other. What that is telling me is the probability of A given B and the probability of B given A, aren't they not likely to be equal to each other except by sheer coincidence? They tend to be quite different results. Cool. Still on conditional probabilities. This is question 13, and I'm just going to write down what's going on here. In an election, 64% were Republican. Okay, so R-E-P for short. So the probability that you chose a Republican was 64%, and I'm going to call that 0.64. And what's the probability that you're not a Republican? And you should be able to tell because I've told you this.
.36.
Agreed. If I put letters around this and I call this R and I call this the complement of R, don't they always add up to 1? So you're a Republican or you're not a Republican, right? You're a male or you're not a male. It's raining or you're not raining. Remember the complementary event things, those guys. So far, so good. So what's the probability? Oh, I forgot to tell you something else. Of those who voted Republican, 60% voted for candidate X. And 5% who voted those who were not Republican, also voted for candidate X. And we are looking at some conditional probabilities here. The first one we're going to look at is, what's the probability that someone voted for candidate X, given that they're Republican? And the next one is, what's the chances that they voted for candidate X, given that they were not Republican? And the answers are these two. Okay. That's not as nice a question as I thought. Let me pick my one. Let's do a two-tier. Oh. Shooting space. I apologize. It's overtime. When we see you tomorrow, you are going to say, we are doing probability trees. So I will know where to continue. And what we're going to do is we're going to show you how to deal with these kind of convoluted questions where 40% did this, but of that 40%, 10% then did this and 80% did that. One of those two-tier, three-tier things, and it's going to be called a probability tree. And it's a nice visual way of answering quite complicated questions. So last name and bye-bye. And oh,